Anyways, yeah. So
Sir, I had one more question.
yes.
Like, how do you write on laptop or your
Oh, so I
computer?
use this. There is some pen tab. This is by some company called Wacom. Okay, it's 3,000. I didn't buy this. I got it from someone, and this I was using it. Okay, Wacom pen tab. So it costs less than 4,000, and it's okay. Yeah, but you can only write. It's just a mechanical writing,
But
and
then you use a pen or what
yeah. So it
for
has a
that?
pen tab. So it has a this is stylus or whatever you want to call it. I don't know
Yeah,
what you
that's
call
what
it.
I was saying. How do you get so perfect handwriting? Because I was
Oh,
trying yesterday with my bare hand on
yeah,
that
with
keyboard.
bare hand it's very difficult. Yeah, I just use this because I have to teach sometimes, so I use this. That's why. And in some interviews and all these days online, so yeah. Okay. So yeah, so it's wrong here. So it's yeah this thing, and it is defined by x to the n. Yeah, and we know that the limit we just said is equal to 0. So show that it is not uniform. Show that convergence is not uniform. So Raghav, you see that the pointwise limit is 0, like for every point.
Yes, sir.
Okay, so that is fine. Okay. Yeah, it can happen because if you miss a class, no, and you are also not well, so it tends to, yeah, that's okay. You'll catch up easily. Just, yeah. So why is it not uniform? Yeah. So you can try to draw a picture also if you want. That's up to you. So like, I don't know, one and so like x is this. X square is lower. And, yeah, this diagram is correct. Yeah, it becomes lesser. Yeah. So
Yeah,
the
okay. So I got an argument.
yeah.
I think so. Basically, what the key thing here is that uh, if you take an x naught, okay, if you take an x naught, then there will exist some n naught. Then there will exist some n naught. But
And not
I
for
can
what?
not there will always exist an n naught such that for all n naught for all n greater than n naught x raised to n will be less than epsilon.
Okay. X
Now,
naught
but
raised to the n is less than epsilon.
yeah, but
Hmm.
the thing is that if I just pick an let's say x naught prime which is greater than x naught,
Okay.
then the same n will not work. The same n naught will not work.
It might not work.
Yeah, might not work. Like, yeah, we can always give an argument why it might not work.
Yes. Right. You can always pick a x naught prime larger than it, which you can always find one's x naught for which this n naught will not work. So
Right.
meaning that not work, meaning that it will become more. But can you say more accurately in how?
Mhm. Okay, how? Mm, mm,
It's also clear from the picture, but again, we have to explain, right? Like you take any x naught, then you pick, let's say, this n naught, this n. But as you go larger, then and let's say
The
this is your
value of
epsilon.
N0 is pushed forward.
Yeah, because it tends to 1. Yeah, as x tends to 1.
Yeah.
For any given n, as x tends to 1, the value tends to 1. And that's clear from the picture. So if this is your epsilon, then you can find an x bigger than that, which is for which the same n naught will not work. You may take some other n naught, but again, you have to just simply give a clean argument. This is just pictures and so on.
Mm. Mm, maybe we can mm,
So this is about forming arguments, really. And but this is usually the first standard example that one should know, and it leads to similar arguments work in other places. So maybe after this, we should do one more example because we are not able to do the calculations well. Means these are like calculations.
maybe we can so so maybe if we take an n which is lesser than n naught.
Lesser than n naught. Okay.
No, I see what I want to
Hmm.
give a formal argument. I want to somehow express n naught in terms of epsilon and x naught.
Hmm. Yes. Okay.
Yeah, that is what I want to do.
So you do that. You can take log or something if you want.
Yeah, that
It's
is
like a
what I want.
bash, but okay. Yeah, it means it's not needed, but yeah, it's okay. It will be a correct proof. So you can take log.
Then yeah, log, you can take log. Then obviously, so n will be lesser than log of epsilon over log of x naught.
But log of x naught is negative. Is it negative? Yeah, it's negative.
If the base is E, it's negative.
Yeah, the base is E, so it becomes bigger, right? I think. Yeah,
Right.
if I'm right. Yeah.
Mm-hmm. Yeah, that makes sense because
Hmm.
that makes sense. Now, if we take a bigger, so at one point this will be equal to n naught, right?
Okay. Yeah.
I'm just trying to make sense of if we take bigger x naught prime, then how will this affect n? It
Yeah. You
will
want.
push the threshold forward, right? The minimum value of n forward.
Yes. Yeah. Like the minimum value is n naught, so maybe we should just keep it as n naught. Yeah. Some n
Yeah.
naught. Yeah. Then we want to take a x for which this n naught fails.
Right. Mm.
You want to take a x, maybe larger x, for which this n naught fails. Means this inequality fails. That is not difficult. Now you have to see it. So what happens if you increase x naught? What do you think?
We increase x naught, then the negative value is still there, but it will increase. So the log x naught, that will increase.
It will become less negative.
It will become less.
Negative, matlab comes towards 0.
Yeah, and
yeah,
so
then it will increase, right?
yes, and the whole quantity is going to go to infinity. Epsilon is fixed. That's all, right? That's a simple argument, right? I mean, the x naught goes to 1, then this denominator goes to 0 from the negative side, but that negative thing gets cancelled. So this goes to infinity, right? It cannot work.
Right.
Okay. Yeah. I mean, more see log, because log is not a trivial thing, right? Existence of log and so on is not a trivial thing. Simply, if you want to say, okay, I let's say you take a n naught, you take any n naught, right? You take any n naught. I mean, you want a x for which this will fail, right? So how can you find that x? Well, the x has to be less than this. For any n naught, the x has to be less than this, which means if you take a x bigger than that, this n naught fails. Yeah. So I take an n naught, I want to show it will not work. I want to find the x. So I want to make this inequality fail. Yeah. And so just take x bigger than epsilon to the power 1 by n naught. Okay. So you just see till what will this inequality hold. And so after that. Yeah, so that is a simple thing, and even from the picture it is clear. But yeah, forming arguments, yeah, because now we are entering into more serious. I mean, you guys are entering into more serious analysis. Obviously, I mean, I'm also trying to learn to do these arguments more peacefully and more simply. So that's okay. But you see, there is a very interesting way to do this, and through that we'll learn something new. Let me give you a hint in the sense that I want it to be done in a certain way. Let's see if we can do. Use the following. Okay, use uniform. Just the last theorem we proved. We don't need the proof, but use this. That uniform convergence. This is like a bash, but it's an interesting argument, and it does work in a lot of places. I mean, it's probably needed in a lot of places. Uniform convergence implies limit is continuous. Use this to show that, see, this kind of thing can be used to show something is not uniformly convergent. Right? You take a very nice property in mathematics and you derive consequences of it. Why? Because when those consequences are not satisfied, then you show that that nice thing doesn't hold. Right? That's the thing. And that's why that's one utility of these theorems. Is try to use this. Let's see. This will be.
And the last time you explained that the class of continuous functions is larger than the class of I mean the class of function, like for example, you take a sequence, it converges to a function, and that function is continuous. That does not imply that that convergence is uniform, but uniform convergence will imply continuity.
Yeah. So just because the limit is continuous, that does not imply uniform convergence. That's why we cannot use that to prove uniform convergence, right?
Right.
But
we can use that to disprove that.
Yeah, because it's a necessary condition. So when it doesn't hold, then you.
It's like using for example, while proving some limit we generally use limits of series to prove this that it is not the limit of the function. So for example, I have a claimed number t, which is the limit at that point.
Mhm.
I do some series manipulations and I say that, okay, so at this, so if I use this series, it converges to C, but the
Huh.
C, but the
If I
sequence
use
of functions will converge to another point. So it will not be, so the estimated limit is not the limit. It is a great tool to disprove things rather than to prove the things.
Yes, yeah, because it's a very good property of continuous functions. And when that property doesn't hold, then you disprove continuity or limit, whatever. Yes, yeah, it's a great, right. That's it's a similar, philosophically at least it is similar. And also, yeah, maybe more than that. Shouldn't just say philosophically.
Actually, that last example we took right now, in that, so f is like f of x is 0 right now, the
Hmm.
for x belonging to open interval 0 comma 1. Now this function is continuous, right?
Yes, this function is continuous.
But it's, we have proved that it's not uniformly convergent. The limit is not I mean the convergence is not uniform.
No, right.
So maybe this can be the example you asked.
Yes, yeah, that's also correct. But now let's try to use this to do this problem. I mean, to show that try to show that the convergence is not uniform by this. But then you would say, what? I mean, the limit is continuous. So how can I use this to show not uniform convergence, right? So if you want to show that it is not uniformly convergent, right? So maybe let me erase this and write more straightforward. I mean, it doesn't really matter. Once you get used to all this, then it's all same. But limit not continuous implies not uniform. Okay, this is what we're going to use. So you would see that here the limit is continuous. So you would say, what is it? It doesn't make sense. But then I would say, can you extend the domain of this question so that the limit, I mean, how would you extend the domain of this question? Just take the close intervals, right? That's a natural thing. So I'm not saying I'm changing the question. No, see, yeah, let me just write this. Consider Fn from close 0 to 1 to R. Now can you same function? I mean, same meaning that you understand that at 1 also we're defining it to be the same thing. Now can you tell me what?
It's not continuous.
Yes, now
it's
it is not continuous. Right. Now it is not continuous. Okay. So, but let's see. Yeah, let's see. Be careful. So now what is fx? So f of x naught, I mean, you know, but I'm just writing it. And f of 1 is 1. So this is x naught less than.
Less than 1.
Perfect. So f is not continuous. So using this, what can you say?
That it is not uniformly convergent on 0, 1 close.
On close 0, 1. That is the thing. But now how do you continue that to? So let me just say that this is not uniform, uniform, or not convergent with respect to the sup norm. Not uniform on this. Can it be uniform on the open interval 0, 1? It's a smaller interval. Is it possible? I mean, a priori, it is possible. It is not uniform on close 0, 1 is clear. Can it be uniform on open 0, 1?
we have proved that it's not uniform.
No, yes, I know, but can we use this to conclude? It is, we are trying to do an alternative proof.
Okay.
Yeah, that's
It is continuous at 1, is it that?
I don't think
It is
that
not
analogy-
continuous at 1. Yeah, it is not continuous at 1. Yeah. No, but maybe I'm saying it the wrong way, right? So, I mean, the way maybe I should try to say it like this. I mean, can you, okay, so here is the question. If, so let me just erase this thing. This is okay. What I'm asking is this, just a fresh thing. Gn is just any sequence. I'm not giving any function. So notice this thing. Means try to answer this question. If Gn is on 0, 1, this thing is uniform, uniformly going to G, yeah, show that Gn to G, assuming that Gn is defined on 0, 1 closed also, Gn to G is uniform on closed 0, 1 also. This is my question. Then you can fit it in that wheels, but I'm trying to say that uniform convergence can be extended to the limit points. At least that's what I'm thinking. Okay. So Gn is a function on closed 0, 1, but on open 0, 1, it is uniformly converging to G. Show that it same holds on the closed also. Okay. So just try to catch this. I'll come in a minute. Drink some water and come. Okay. So is this this seems to be intuitive, right? Maybe I don't know. Okay. Okay. I mean, I should just say that Gn is continuous. Maybe I did not say that, right? I should say Gn is continuous. Yeah. Yeah. I that is Gn is continuous. That is
Sir,
the
can
only.
we try the contradiction maybe?
Okay. Yeah. You can try. Yeah. So this is the only question now we are doing. So we just erase all this. I mean, if you can do this, then you're done, right? Because if you can show that the uniform convergence can be extended, then you are done. Because if this was uniformly convergent, then on the closed interval also it will be uniformly convergent, but that is not the case. So we are done. But so how do we? Okay, let me also just give me a minute. I'll just think about the hype because I'm not sure about 100% sure about it, but let me just for a minute. Just then we'll. Um, so just 1 minute. Let us try this together. Okay, so then we can understand. Yeah. So really, I should just update the question a little bit. So because Gn is on 0 to 1, yeah, Gn converges to G pointwise on 0 to 1, and Gn converges to G uniformly on open 0, 1 is Gn to G uniform on close 0. Gn is continuous. So this is the question. Okay. So let us write the uniform thing, condition of the uniform on close 0, what, let's just write what we are given. So, I mean, epsilon, we understand, arbitrary epsilon. This thing is less than epsilon for all x and for all n bigger than some and naught. Okay. Just another way to write it is, if you can, if it will, some idea, supremum of gnx minus g is less than epsilon, supremum over x, and this x is in obviously in close 0, 1. Can we say anything? Yeah, this is, I've just written what we are given. I have not done anything.
Yeah, but we can now try to use our previous results which we have
Hmm?
proved. If,
Right.
if Gn is uniformly convergent to G in open 0, 1, then G is continuous on open 0, 1.
You're right.
Now, why should this imply that so if G is not continuous on close 0, 1, then there is no question of uniformness on closed interval.
Right.
So that must not happen.
Yeah. So
But
G must
why
be
is that not happening? Like there is something which is forcing that to not happen.
right.
We must find that. That is the,
Yeah.
I guess,
But
further problem.
it might happen that the answer to that question has to pass through the fact that the last statement is true. Right. I mean, you understand. I mean, that truth which you are talking about may be proved. It may be possible to prove that only via proving that this uniform convergence is holding on 0, close 0, 1. I don't. Yeah. So sometimes that happens, right? I mean, something is true, but it will follow only when you, maybe possible independently also we can prove.
Yeah, but that is clear that G must be continuous on close 0, comma 1.
If we prove this last statement,
Right.
otherwise it is not clear.
Yeah.
Yeah, or I mean, yeah, means if you can provide a counter example where the limit is continuous on 0, comma open 0, comma 1, but not continuous on the at 1, and the convergence is uniform on close, then this question is wrong. I mean, then the answer is no. Yes. But let me say that let's say it is true, right? I mean, let's say it is true. See, basically, see, this thing is holding for all x in open 0, comma 1. Now you just want it to hold at 0 and 1 also. What should you, okay, let's forget about 0. Let's say at 1 you want it to hold. Then what is the, as you have said, and I mean, Raghav, you see the G is also continuous. That is true. That is what we, as said in the beginning of the class.
Yeah.
The
So
limit.
basically, okay. I think I'm getting at what you're hinting is that if G is continuous, then we can always say that G will be continuous at 1.
Why?
No, yeah. Again,
That is
G is
like
continuous closed interval. I'm again using the
G, and even if you prove G is continuous, that doesn't independently, that doesn't mean that.
yeah. That doesn't mean that, but
I understand. Yeah.
we can. So basically, right now we need to prove that Gn of 1 minus G of 1, this should be less than epsilon.
Yes. And
for
why
the
should this
same
not happen?
n0.
For the same and not if you want, yeah. But why will this not happen? You just take the limit. I mean, you will get equality. Yeah.
Sir, for our case, I think it is true.
Meaning?
The xn case, then this is true.
X to the n case.
Ah,
No, so in the x to the n case, the convergence was not uniform on close 0, comma 1. Right. Yeah. And I mean, yeah, so we, right? First thing, it was not uniform on close 0, on open 0, comma 1. And that's why it cannot be uniform on close 0, comma 1 from this statement. Okay. Or if you get confused, then leave that x to the n thing for now. What I'm just saying is that this is true, and it's simply you have to take the limit. If you look at this quantity and why, what is special about 1 here? It's the limit point, right? And you can take the limit in this inequality, right? Because these are continuous functions, right? I mean, or just to say that because the limit exists, it doesn't even have to be continuous.
Yeah,
The
but
limit
then
exists.
why I don't see why it will work with Gn of x, but why should it work with G of x?
Right. Yeah. So that seems wrong. Yeah, that's right. G of x could be.
Yeah, we know that G is defined at 1, but we don't know if that like the limit is equal to G of 1. You don't know that because it again you invoke continuity if you directly use the limit, right? Yeah.
So that is okay. So maybe that is incorrect.
So then
Right.
you need to prove that G will be continuous in that closed interval somehow,
and
and then
no.
maybe you can use.
Yeah, that's right. We could do it. No, so then we will not do it. Then basically, maybe what you can then do is, I mean, G is a Gn does converge to G pointwise on 0, comma 1, right? So you
Right.
know that, so you can take the larger of that kind of trick you could do. Epsilon for all n bigger than some n1. You take the larger of n0 and n1.
Oh, okay. I got it. And then it
then it will
I
work
got it.
because just finitely many points if you
And for, so for every epsilon we have to do this, so we have to always check which is larger and set that and not with that, so basically that epsilon and not pair will form.
yes, right. I mean, you don't have to check. You to
You
just
don't,
say that.
yeah, but this is all arbitrary, so it doesn't matter. But if a computer processes it, then it will check for every what is greater, and then it
Take
will
the
make a
max.
pair.
Right. Yeah. But if it was told to you, so this will always work if you have uniform convergence on all but finitely many points.
Right.
Right. If I remove some finitely many points, it's not a problem. But this, but if it was further told to you, which I sort of mixed up, yeah, because this is just something I tried to think of. I might have used it some point earlier, but point is that if it was also told to you that G was continuous, then you could simply take the limit.
G was continuous on closed interval.
Yeah, right. If it was additionally told to you that G was continuous on the closed interval, then you could take the limit. Right.
Right.
I mean, and
But
that
this
you
also
could.
implies that, so this method also implies that we can just say that if Gn converges uniformly to G in open 0, 1, then G is continuous in closed 0, 1.
Yes, that's right. And G is continuous. That's what we have proved, right? And it's uniformly continuous because it's closed. That's a yeah. No, but I'm saying
So
that the
now,
utility.
now here from uniform convergence we go to continuity. That uniform convergence again implies continuity.
And then the continuity implies uniform continuity also because you are on closed 0, 1. But that's not important to this point. Yes, yeah. Again, using uniform convergence you can do. But what I'm saying is that this could be game changing in the following way. Like if it was like Q, I mean, here there was only finitely many points, but we can use this idea. Suppose it's from Q to R, and Gn is no. Sorry, this is again wrong. I'm saying I'm just making these changes, trying to see, and it is pointwise convergent on R. Let's say, okay, and uniformly convergent on Q. Okay. Then the question is it convergent on R? And given that G is continuous on R, G is yeah. So maybe this could be a homework question. Okay. Yeah, you can note this down, but note the hypothesis. Yeah. So the sequence is continuous on R. The limit is also continuous on R. Uniform convergence is given only on Q. Can you lift it to R? Now you cannot use the finitely many points trick. But just note this down and you can try this for homework. And yeah, try more questions. Kaczor is there, Berkeley Problems in Mathematics, many books, and just Google. Yeah. Rudin is obviously there, Bartlett and Sherbert, they have problems. You should try that first actually. Okay. So note this down, and Raghav, if possible, you try to prove the statements, or you can just have a look at the video if you want, or you can read from Bartlett and Sherbert if you can follow it. Okay, last test thing. Yeah. Okay, if you need anything, also send me a mail. Okay. And then we'll meet on Sunday, 8:15 p.m. Okay. So then the meeting will end now. Okay. Thank you. We did these discussions. Okay. Bye.